Hello. Okay. So, good evening, everyone.
Good evening, sir.
Okay, I think yeah. So, so today's discussion is about week 10, right? So week 10, which is I think it's is how we can reach to the support vector machine solution, right? Or what is that support vector machines? I think about that. In that week, I hope all of you have already completed your MLF course, and if not completed, at least I think we are in week 10, so that means there are also around this constraint optimization and optimization topics will be covered at least that because to understand this, right, um, why we are like how what is this maximization of margin and all, we need the understanding of constraint optimization uh, as well as the unconstrained one, right? The primal solution, dual solution, so or maybe primal problem and the dual problem. All of this is necessary. So I hope all of you at least familiar with the KKT conditions. What are those KKT conditions? Lagrangian functions, and I think what are the like one of the KKT conditions is what the complementary slackness conditions, right? The first one is let's say if L is your function, Lagrangian function, the first condition is what del L should be equal to 0, and the second one is complementary slackness. The first one is called as a stationarity condition. The second one is complementary slackness, right? Uh, I hope all these terms are at least you guys are familiar with that, because these terms are useful, or these things are very useful while understanding uh, this SVM concept, right? How many of you have watched the lectures? You can just thumbs up, that's fine. Or you can, if you wanted to speak, you can speak also. No, not at all. Okay, Vivek is done. Aditya. Okay, Abhishek is not. Oma is saying not. About others. Yes, we. Okay, Vivek. Only first one you watched. Okay. 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 No issues. Let's then. Yeah, first half. Okay. Fine. Okay, I'm assuming that not all of you have completed, so only few of you. And have you understood the lectures? Those who have completed the lectures, do you understand how this problem has been like solved, right? So not everything explained explicitly. What I feel, just like not explained in the sense not solved it right completely. The final solutions are given, and we are also interested in that only. We don't need like every step to solve the problem, uh, right? So we just wanted to understand what is it, right? Exactly, what is the meaning of support vector machines and all. Fine. So let's start then. Yeah, let's. Okay. So in the previous week, what we have learned. So okay, you guys also have to contribute into this session. Okay, you'll have to speak when because that will make this conversation uh, good enough, right? So yeah. Otherwise, I will also feel that nobody is only people are listening, and I'll have to speak only, right? You can tell me maybe if I ask some questions in between of, or if you have any doubts in between, you can just let me know. Fine. So previously in the perceptron algorithm, what you have said, or what are the things in the perceptron algorithm you have discussed? Okay, first of all, what are the assumptions, right? What were the assumptions in the perceptron algorithm? First one was
Linearly separable data.
yeah, linearly separable data. Yeah, regarding this, when in the solve with us session, right? The previous solve with us, I think I said about one thing, right? The data is linearly separable or not. There was one option in one of the questions of solve with us. So yeah, so it should be. I think it should be linearly separable, right? So, uh, right?
So that was for regression, logistic regression,
Logistic
right?
regression, right, right. And that should be linearly separable. Even that logistic regression is there, it should be linearly separable. Okay. Okay, here it was perceptron algorithm. Linearly separable data is the assumption, right? What does that mean? You should be able to find a W such that, uh, let's say, what is it like? W transpose X should be, or W transpose X equal to 0, right? So that line.
Let me add W transpose X into yi.
So
Is more than equal to gamma.
no, that is okay. Later on, we put that condition, right, of the gamma. Initially, we said that the data is such that so there is no outliers, right, as such. What we are saying is there are positive data points on one side and the negative data points on one side. Correct? There is another thing which we said is what radius assumption, right? I think radius assumption was there. What was that?
Norm of xi should be less than equal to the radius
Outermost point should be
outermost data
maximum
point.
R. Outermost data point should be radius R.
It should be what there
Less
should be
than equal
less than or equal
to
to r square.
r.
R
Yes.
or r square, right?
R square.
It's a
Yes, sir.
right, no? If you are taking the length square, basically, it should be r square, right? So that means what? Like if you have the data such that what are we saying is, let's say you have let's say all these positive data points here, right, and all the negative data points, let's say in this side. This data set is linearly separable, definitely. The what we are saying is, let's say this is the outermost data point, right? You are saying that all the data points actually lie within that radius, right, or within a circle. Is that fine? That was the I think that was one of the assumptions which is called as a radius assumption. What was the third assumption we are having?
Norm of W is 1.
W
Uh,
star.
Norm of W is 1.
okay, norm of W is equal to 1. What does that mean? We are just saying that
The vector which W
yeah,
is the length of the
W we have restricted it to 1, right? Right? Okay, fine, right? So that was one thing. And in perceptron algorithm, so what we have assumed that this is not going to work, right? Even though all these assumptions are there, this is not going to work. What we said is we have put one more thing which is called, let's say, uh, what is that? The margin, right? Because with this case what happens, it may not converge, right? That was the problem, and we introduce one more thing is we'll have the margin, correct? So uh, if you have, and what we said is if you have the margin as high as possible, then what happens is this algorithm will converge
in
fa-
fewer steps.
faster, right? Yeah, it will converge in fewer steps. So that we called as number of mistakes, and number of mistakes will be less. That means number of steps to like, and it is upper bounded by
R square
R
by
is
gamma.
equal to gamma square.
r square by gamma square. So here the gamma is very gamma plays one important role. So this, let's say if this is W, then this will be what, this line will be W transpose X, and what we are saying is there exists some margin, right? So it should be like bounded by this, right? So this gamma is, so this will be all okay. This line represents what all the data points on that line will be
W transpose X equal to
W
gamma.
transpose X
Greater equal to
equal to
gamma.
gamma. This is equal to gamma, and all the points on this side of the line will be W transpose X
Greater
greater
than
than
gamma.
gamma, right? And here, all this, so all the points on this line will be
W
uh,
transpose X equal to minus gamma.
W transpose X equal to minus gamma, right? So these are the lines. These are the two lines. This line is W transpose X equal to 0, right?
Sir, but the
Yeah.
distance from the origin to the line W transpose is equal to gamma. The distance is not necessarily gamma.
If W equal to 1, then it is gamma. If norm of W is equal to 1,
Yeah,
Yeah,
Yeah.
when
So this
when
thing,
norm of W is equal to 1, then it's
yeah,
gamma.
yeah. So all these assumptions we are actually saying, right? So this should be there. If they are there, then this will satisfy, right? So we are actually taking a unit W. If you change the W, then it will be the
Okay,
values
so it means the distance is gamma.
right, correct.
Okay.
So if it is a unit length, then the distance from this line, right? So this W transpose X and 0. What is this distance then? It is gamma, right? Fine. And similarly on the other side also it will be gamma. Fine. So these were the things, right? And we were saying that in the perceptron algorithm, what was the another thing is that, okay, what is the, how we are going to separate this? Like it will be like, if you have a W star as the solution, it will be W star transpose Xi Yi. What is this? Like this was the update rule, right? Anyway, like we are going to update, and this should be greater than or equal to,
Greater gamma.
Gamma.
yeah. If this is there, then my data set is able to like separate these two classes, right?
Yes.
And
W is able to separate the class.
yeah, right. So W is able to separate the classes, right? And this gamma should be strictly greater than 0. This was my solution for the perceptron algorithm. But now, what is the issue we can encounter now? Or can we get different W's for this problem?
Yes, sir.
Yes.
Right. So we will get different W's with the same data set, right?
Yes,
Okay.
sir.
So suppose you have this data set here. If you have this positive lines, and if you have negative, and whatever the conditions we said earlier, so if I use that condition, suppose if this is my data, okay, this is my, let's say, W, then which will be the line, this is the line, this line represents what?
W transpose X equal to 0.
Yeah, this is W transpose X equal to 0, and with margin, what will be the okay, which one? So this, the margin should be parallel, right?
Yes,
This
sir.
line, suppose this is the margin. So is this a solution?
Yes, sir.
Yeah, it can be a
Yes.
solution, right? It can be a solution. Okay, do we have any other solution than this?
Yes, sir.
Yes,
A perpendicular one.
let's say if I have this one, okay, and with this, then this y-axis will be your here, right? So let's say this is W uh, prime, then this will be, this line will be W prime X transpose X equal to 0.
0.
And can I have this margin then, right?
Yes, sir. Margin will be
Yes,
reduced.
sir.
So we will have this margin, right? So all the data points over this margin, uh, we can consider, and now they will have, let's say, but this gamma and this gamma will be different, right? So let's say this was one gamma, and let's say this is going to be another, let's say, gamma prime. Is that fine? These two will be different ones, but which one should I choose here, right? That is the problem now. I have more than this? Possible, right? So we have more than that, but again, what we said in perceptron is the number of mistakes. What does that mean, number of mistakes the perceptron drew? Like how many times we are going to update it, right? It depends on what? They were upper bounded by r square upon gamma square. So what does that mean? If I have gamma higher, what does, what it will do?
Mistakes will
Lesser.
be less.
Reduce the mistakes.
Reduce the mistakes, and in
Number
that,
of iterations.
yeah, in that process, the number of iterations or the number of updates will be uh, lesser, right? And that leads me to the faster convergence of this algorithm. So so now the problem is, or what I need to find out now, uh, that optimal gamma also, right? If I get that optimal gamma possibly, then definitely, so I have to choose one of those W's such that this gamma will be as high as possible, right? And then that W will be what? The optimal solution to that problem. Is that fine? uh, I think that should be no issues, right? Correct. So
Yes, sir.
so now my uh, the Now the problem is now, or the question statement or the goal to this problem will be what? The goal will be what? I need to maximize the margin, right? Correct?
Yes, sir.
And if in doing that, what will happen if I maximize my margin? In that case, I will, so whatever W which maximizes that margin will be my optimal solution to this problem. Okay, so can I formulate this problem? The formulation will be like this. What do you wanted to do here? Maximize gamma for that W, right? Correct. And this will be this thing. And what will be the constraint over here?
W transpose xi times yi less than equal to gamma.
Greater than, right?
So
Oh,
this
sorry,
means find a W that maximize gamma.
Huh?
This maximization thing,
Huh?
is it means that find a W that maximize the gamma?
Or can you just, okay, in other way around also you can say, right? Find the maximum gamma such that your W will be optimal, right?
Yes, sir. Yes.
Correct. No, if I have that maximum margin, then the W corresponding to it. So we have this. Let's say you have this W and this W prime. So how will I select the W between these two? So if I find this gamma, which is the maximum one, the corresponding W will be this, right? So that will be my optimal solution. Okay. So
Right.
The one question here.
yeah.
Perceptron can using Perceptron,
Hmm.
we can get either of these W's. It's
Yeah.
not necessary that we'll get the optimal W, right?
No. Because how does perceptron will work? So I think we have seen some problems in the solve with us. So one thing was it is dependent on what? Initialization, right?
Yes.
If you initialize differently, you might end up into different W's, right? And what else? Another thing is order,
Order in which you choose the points.
right? Order of data points. So if I choose this order, it might end up in different W. If I choose this order, right, it might end up into different W with the same initialization.
But
So
now my second question is,
yeah,
the gammas corresponding to these two W's are different.
yes.
Uh, so, but if we run Perceptron on this problem,
Hmm.
there should be the upper bound for the number of mistakes that we make
Hmm.
will be decided by which W? The
It
blue
no.
W or the black W?
Okay, so number of mistakes depend on what? Gamma square, right? Like
Yes,
inversely proportional to the gamma square, right? So
yes,
it doesn't matter. So what happens is perceptron says that okay, or why this condition says that this condition came into the picture to say like to show what? The convergence of perceptron, right?
Perceptron. Yes.
Like it is not saying that how fast it should go, right? Or I need the faster one. See, if I choose this gamma by perceptron algorithm, that will give me the finite number of steps, right? Or finite number of updates or finite number of iterations to
Yes.
converge, right? If I choose this gamma, it might give me more number of mistakes, but eventually it will converge, right? So it is not giving me the optimal solution as such. It is giving me some solution, right? Or that solution which separates this data points.
But
Fine.
the mistakes which suppose we get the if I get the one solution and you get another solution,
Yeah.
will we make different number of mistakes to get our
Yeah.
solution?
Yeah. Right.
Or
But
or the
yeah,
or
we
the
can.
upper bound is common for both the
No,
solutions?
upper bound is common, but that see upper bound tells me what? Let's say the number of mistakes will be at max 10, right?
Okay.
So for me, let's say I have done like 5 mistakes, and for you, you have done let's say 4 mistakes. Fine.
Okay.
Are we both in the same set of like that thing? Like yes, right? Because we are satisfying that condition that the maximum number of mistakes I can do is 10. Even I do 5 or you do 4, right? uh,
Okay.
Both we are satisfying that. So anyway, we are getting some solution. So
So
five
that
mistakes.
10, how do we get? What is the formula for calculating that 10? R square by gamma square, right? But
Yeah.
gamma, which gamma we use there for calculating that 10? Because the gammas corresponding to these two
Huh.
W's is different.
Different. Yes, yes, yes. So yeah, okay. So that is another thing, right? Let's say you are choosing only this W in case. Fine. Me and you
Okay.
both are choosing the same W. In that case, your gamma will be same. So number of mistakes will be upper bounded by this 10. Now what you did is you started from this order, right? And I started with this, or I started with some different initialization. You started with different initialization, right? In that case, our number of mistakes are bounded by 10, right, for both of us. The
Yes.
only thing you might end up in lesser number of mistakes depends on what, these two factors, and I
Yes.
might end up in different mistakes. See, this thing will be applicable only if uh, the same gamma, if you are choosing, right? If you have chosen different gamma, then I shouldn't compare that, right? Because the upper bound for both these things will be different, right?
But the problem is the same, right, sir? You got a
Problem is,
different
yeah, yeah,
W.
yeah, that is true. But then we cannot compare, right? We cannot compare the number of mistakes in that case, right? If you choose different gamma and if I choose different gamma, right?
But sir, optimum W is in terms of robustness, right? So we will choose W because in the future some data can
Correct, correct. So X test will be, let's say, something else. Then it should be able to, let's say, if
yeah,
it is
this mistake will up to the training
correct.
period. After that,
Yeah,
it
let's
will.
say if any data point lies here or lies here, right? What will happen, right? So that is the thing. So now if I go with this, it says what? It might
Yeah,
say
it is
negative,
minus. Yeah.
right? And it might, and with this line it says positive, right? So yeah, that is correct. So you need the robustness, and that's why the perceptron algorithm doesn't provide you that, right? That's why we need to see something more, correct?
Yes, sir.
Because, sir, why I ask this question is there is one activity question based on this.
Huh.
Uh, there is a optimal W, and then there are two W's which different perceptron algorithms find for that same problem.
Okay.
But they are saying that the optimal W decides the gamma. According to the answer of the problem, it is the
Okay.
optimal W which decides the upper bound of the upper bound of the number of mistakes.
Okay. Okay.
That's
But
what they are saying.
then what is optimal W that has to be said, right?
In that question, optimal W has also been given,
Huh.
and two other Ws are also given, which two different people have found using different approaches to the perceptron algorithm.
Hmm.
But it is saying that the upper bound is decided only by the optimal gamma.
Optimal W, right?
Yes,
So
yes,
let's say
yes.
you have, okay. So optimal W is like where you should be. So I think, see, optimal W in the sense, I think it is able to correctly classifies all the data points, right? How will
So,
you
so
see it?
what I get gather from this is that the optimal W can only be found by this vector method, which you are going to now say. Perceptron will not give us the optimal W. That's what I understand. I understood from the lectures.
Perceptron will not give you the optimal W. Is it that you're
May
saying?
not give you the optimal
Yeah,
W.
yeah, yes. Correct, correct. But that is why we need something else, right? Like perceptron probably is like, see, optimal W in case of perceptron is like dependent on a lot of assumptions, right? Okay, this is the thing, this is the thing, this is the thing, and then it will be able to. So, but how this gamma is, like, we should give some conditions about gamma, right? What is that gamma? Only on, if you fix that part, then only it will be giving you some values, right? Let us try to see this. Maybe we'll come to the conclusion over that. Maybe I'll see that question also, whatever you're saying. But currently, do you feel that there are certain issues with the perceptron algorithm, right? uh, and how we can be able to address those issues will be this thing. One more thing is, I think, okay, what I said is this is the case, right, in perceptron algorithm. correct? So this will be the case, right? Optimal W is that W which, what is it, like correctly,
which gives the maximum gamma, right?
yeah, which correctly, or maybe which correctly classifies the uh, data points, all data points, right? Using this margin, correct? So it is not here. It is not mentioned about any quality of that gamma, right? Whether it should be maximum, whether it should be minimum, that is not mentioned there in the perceptron. That's why we wanted to work on that, right? Like
But sir,
what? Hmm.
all the W's we get through perceptron
Hmm.
will correctly classify all the data points. All the W's which we get.
Yes, correct, yeah, all W's will get, but that is not necessarily what is your the optimal solution, right?
Yes.
Means optimal
So
solution will be which one, where
with the maximum gamma, with the
gamma, yes,
maximum.
yes, maximum gamma, right? So that means you should have the gamma as maximum as possible, so that the number of mistakes will also be lesser, right? In like this this case is like upper bound, but that doesn't guarantee you the, let's say you said the upper bound is 10 and you have reached to the solution by ninth uh, ninth iteration. Will that be your correct gamma, or no, not correct gamma, will that be your optimal solution, right? That also is the case, correct? That might be some other W which is not the optimal one. Optimal one also should get the number of mistakes lesser, as less as possible, right? Yeah, and that is decided by your gamma, correct?
Yes, sir.
Okay, so what is our goal now? To maximize this margin, which is gamma, right? Maximize the margin, so that you should get some, let's say optimal W in this case, uh, right? Okay, but what is the issue with this now, with this part also? And what else we can say about it from our previous discussions about perceptron? uh, okay, what is the thing here, like okay, what is the issue with this part now?
We can get multiple W.
Right, so we don't have any bound on W, right? So it can give me, because if you wanted to solve for maximum gamma, and gamma is again dependent on this constant, right? So this is the constant optimization problem, this is the constant, right? uh,
As you increase the norm of W, the gamma also increases
right, so yeah, so and how much it can increase now?
infinitely.
Infinitely, right? So that means if you so what does that mean is, you wanted to see the graphically, so it will be like this. So yeah, I'll just use the same figure here. So this is the okay, sorry, this is not the correct one, but yeah, you understand, right? What is this? This part is, let's say if this is W, this is W transpose X equal to gamma, and this is W transpose X is equal to minus gamma, right? These are the two parallel lines. What happens here now? Uh, okay, and will this W be fine, right?
Yes, sir.
Will this W be fine?
Yes, sir.
Right. So any W which is on this line will satisfy this condition, right? Correct. And but
Yes.
what happens if I increase the scale of this W?
Gamma will also increase.
So can we not say that smallest W should be greater than
Correct.
gamma? I
Smallest
mean,
W should be greater than gamma.
yes. In that case, this thing will not be happening.
Smallest W is
W transpose X is a
uh,
scalar value. So
yeah.
that the smallest of them,
Uh,
the for I xi,
mhm.
should be greater than uh, gamma.
But
But we define gamma by that, right? W transpose X is equal to gamma.
so okay, what is this quantity actually telling me? What W transpose X? Okay, this is a scalar, that is true. But what is this? So you have, let's say, this points, right? Like
It's a
x1,
projection of that point on W.
right?
Scalar projection.
Right. So these are
Yeah,
all,
scalar
let's say,
projection, right?
it is x3 and x4. So what we are doing here is we are actually, yeah. So we are actually projecting all of them, right, onto this,
Yes, sir.
right? Let's say, and now you are saying that, and what does again? It is like a combination, right? So it's this kind of a sum, right? Like W transpose x1, all of this scalar quantity, if I make a sum, and what you are saying is it
The
should be
smallest of them should be greater than gamma. Let's say x1
okay.
is the
Let's
smallest one.
okay. So that is basically this projection will be, it will not be a vector basically, it is like some constant, right?
Yeah,
Because this is x
Scalar projection.
W
Scalar projection.
transpose, huh?
yeah,
Yeah, it's a
scalar value.
scalar, some scalar value, and you are saying that if it is, it should
Gamma
be
is
equal.
also a scalar value in that case. Also.
And how will you compare? You are saying, okay,
The
what is
smallest one.
the smallest one you should take? You shouldn't consider the other points on that line. You are saying,
Yes.
uh, okay.
Will it not solve the so much of calculations and all that?
Okay, so no, it's not about yeah. That is true. Basically, we are anyway going to think on that line only. The support vector machine gives me that almost that kind of solution. But the thing is, okay. So you're just talking about this point, right? Here in this side, but we have some negative data points also, right? Here. So you will have to consider all the things, and you are saying that only the smallest one you will have to pick. Correct.
Yes. Either positive or negative. The absolute value, actually.
Absolute value, and you're saying that that should be your maximum margin.
Yeah.
Okay. And how will you choose the W then? Let's say I have some different W here. Now I'll have like a lot of W's here, right?
Yes. Okay.
Okay. So now what happened? Like which one is the smaller uh, margin right now? Which should I pick? Right?
Yeah.
Now I
Got it.
understand the problem, and that is the problem here, right? So when I said one, if I know already what which is the good W, then definitely yes, what you are saying is correct. So that is what we are defining here, right? W transpose x equal to gamma, and we should throw away other points. Definitely, that is the correct problem to solve, and that is what we are trying to achieve here. The only thing is, which one gives me the what is it? The smallest, this one, right? So that projection, correct? Like let's say W transpose x1, let's say x1 is the thing, which one gives me that smallest projection such that the margin between the margin should be what, like as high as possible, right? Fine.
Sir.
And this is what my problem is. I think we are fine with that part. So we need to solve that that thing, right? So we need to choose among all these w's which one is the best w to do that. Fine. That is my problem.
Yes, sir.
Okay, so now the next question is, okay, so this was the problem for me. Let's say I can actually select any W, and any W is actually, what is it like? W is a vector, right? Kind of a vector. We can choose any anything, like let's say 2W, 3W, 4W, and that should satisfy the condition. But that will give me like since we are actually maximizing the gamma, and which again it's dependent on W. So as my W increases, let's say 2W, 3W, that will lead to increase in my gamma, and this mathematically, since I'm maximizing this gamma, that should go to infinity, right? So I don't want to uh, like do that. So what is the next thing? So
Fixing the norm of the W as
yes.
one.
So the solution to this is fix this, and now say uh, like I'm just fixing this norm W1, and then I'll say that this is going to be the case. Okay, so if I say that if I fix this len W, I think that problem will solve for me. But what is the next problem now? How to solve this, right? Like okay, so the next thing will be what? A similar problem is there. Let's say So this will be x. Now we had this part, this part. Okay, I think all of you know, right? So what is this?
So the sir, every comparison, so that we will get new W. So we are taking the direction and reducing the length.
Yes, yes, correct. We'll have to take the direction and reduce it to, like, we just normalize it, right?
Yes,
So
sir.
this is all possible solutions for W, right? Now we have restricted it to unit length, right? Correct.
Yes.
So previously, let's say without restricting it, what was this solution here? So it was like W transpose X equal to some gamma, right? Let's say, okay, I'll use the same example which is there in the lectures. So let's say this gamma is anyway the scalar value. Let's say it is 5, right? And let's say we have another solution. So see, we can get how many solutions we can get here? Like infinite again, right? When it's
Infinite.
like circle. So that is fine. So one more thing we can get, let's say like this, right? And what is this? What is this line? So this line is W transpose X equal to 3. Fine. Uh, I hope this is okay.
Yes.
Depending on the like on and both of these lines are actually what they are doing. They are able to perfectly classify it, right? Classify the data points. The only thing we are worried now is which one is the best one, right? Okay. Anybody says start my which one? DSA session. Okay.
PTS, I guess.
Yeah, okay. I think you can go there and right, and you can watch it later possibly. Right. This was not like I think from for Monday. This is the session timing, right? Or is it like 6 to 8 previously?
Yes, sir.
6 to 8.
Yes, sir.
Okay. Okay. Fine. Fine. I thought this is the timing. Okay. Fine. Okay, we'll see. Like from next Monday onwards, maybe this week. I think we have to complete week 11, 10 and 11 both, right? Okay. Fine. Okay, that's okay. So if I restrict it, so let's say,
So, sir, one more question.
yeah,
Sir, this gamma value, we are taking it for our from. I mean, we are fixing it. We are not getting it from the data, right?
no, we are getting it from the data only, right? We wanted to find the maximum gamma, which is so okay. How this gamma is dependent on? Can you just tell me, like this gamma is a margin, is dependent. Like you can see right from the diagram itself, it is dependent on what W, right?
Yes.
Or you can think it through also. This also. If I just multiply, if I take all this W
And
transpose X,
if we reduce the value of W, I mean, we normalize it, then the gamma will be gamma is also we will divide it
we'll
for
have
with
to
the,
change it, right? We'll have to change it, correct?
yeah, the
So
new
how?
gamma will be gamma by norm of W.
Right. And what that should be, right? You're actually thinking on the correct line. What that should be, right? So now this was a problem for me. Now I just reduced the W. So let's say for this blue line, this was my gamma. Okay. So not gamma. This was the W for this gamma. Fine. If I wanted it to slash it down to 1 unit length, how that will look like?
Divided with norm of
Norm
W.
Norm
of
of
W.
W, right? So there is another part to it. Like instead of doing that, what we are going to think about it is like say we don't do this part. We don't normalize it to 1 because it will like unnecessarily putting all the constraints, right? Like now that problem became maximize over the gamma such that this has to be satisfied plus this length has to be normalized to 1, right? So the
Yes.
final thing is we wanted actually this length, this distance as far as possible, right? This is the margin, correct? Correct.
Yes.
So I wanted that margin as high as possible. So can we do something else? Can we put the restriction on gamma itself? Okay, right? If I wanted to put the restriction on gamma, let's say we should give some number, right? This has to be like this. and will that work for me, right? So, and that will work anyway, because that will automatically reduce the length of W. Fine. So suppose if I say that my gamma is 1, I'm restricting my gamma as 1. Fine. What will happen then? This 5 has to become 1. How does this 5 will become 1?
Divide W transpose X by 5.
So can I say that, like, I'll just divide it by 5 and I'll get 1. So similarly here, if I wanted 1 here, what I'll have to do? W transpose or W by 3, right? Transpose. Now, will that solve my problem? Yes, it will solve, right? So what we are anyway, see what initially we said, to reduce that problem of getting like 2W, 3W and that, we said we should put some condition on W, right? So that means we are saying that it should be in a enclosed circle. What now we are saying is, instead of that, what we say that the margin length, right, that should be restricted to 1, right? Now you, if for that one, what will be the value of W? So
Sir, but
yeah,
we are still
We are
getting.
left with only one constraint now, W. Gamma is no longer there. That is the
yeah,
thinking, sir.
you can think of like that, right? So we are
We are
not
left with only one constraint, that is W
yes.
now.
See, solving for two variables will be difficult than solving for one, right?
Yes,
A-
sir.
and we are doing that now. So now, since we know, see, gamma anyway is dependent on W, right? So if I restrict on W and like think about for different gammas, what we are saying is, for entire, like if you wanted to search for W, make sure that the length, like the margin, right, that it should be equal to 1, right? Now if I wanted that margin to be 1, find such W for me. Okay, so now that is the problem. Is that fine?
Sir, but we are still getting different W's
No,
because here
will not get, no now.
we have two W's here. One is W divided by 5,
Yeah, yeah,
the
correct, correct, correct,
another
correct,
one is W divided by 3.
correct. Now
So,
now what is the thing here now? This, that's correct. Like it's not 2W, you can get like again like so many, right? So many W's will get. It's not like this is the two which we are seeing in this, but any W can satisfy this, right?
so even though we have put constraint on the gamma,
Hmm.
we are still getting different W's.
Correct, correct. So now what is our goal should be here? To get optimal W, right?
With the maximum gamma.
Correct? Fine. So optimal W, when it will happen? The
When
gamma,
gamma is maximum.
right? So now I, instead of that, what I'll say is the width on W is maximum, right? I'm removing gamma now from the uh, thing, right? So this is the case. Width of W. What is width of W? Which is the width of W here? Or width of W is like, it's a width which is dependent on W. Fine.
So I have one question. So the
Yeah.
width of W should be maximum, or the gamma should be maximum.
Same thing, right? So this
But
is
we have already put gamma to be 1.
yes, gamma is 1. That doesn't mean that okay, what is that gamma 1 says? Okay, let me put it in this way.
Because my confusion is the number of mistakes will be R square, the upper bound, because gamma is
No,
1.
no, don't think about that now. Like, okay, that upper bound is not an issue right now. See, I think you are thinking that way, but don't worry about that. That perceptron algorithm is not the case here. But still, if you wanted to think in that direction, so what we are saying that gamma square is 1, right, for everything. But that is only giving me what, like number of updates, right? How many number of updates is
For
giving me?
this, we have already said that the norm of W is 1. We have assumed that the norm of W is 1. That is how we are getting R square by gamma square. So here we are not putting bound on norm of W.
Correct, correct. So we
Yes.
instead of, we removed that condition now. Like norm of W should be equal to 1. I am removing that. What I'm saying is, instead of doing that part, what we are doing is we restrict gamma. So we have two choices here, right? What is one choice? Either put this equal to 1, right? Or make gamma equals to 1. anyway these are interchangeable, right? Do you feel that these two quantities are like dependent on each other?
Yes, sir. W is dependent on gamma.
Gamma, right? So
Yes.
correct. So shall I take these two and solve the problem, or shall I? So okay, I'll tell you, like maybe generally how you solve any problems will be like, say x plus y equal to 2, and let's say 2x plus 3y equals to 5. How do you solve the solutions? You have these two variables here, right, and two solutions. How do you solve it?
You
you
cancel out
you
one.
So
you try
cancel.
to
Yes.
find y, right? Let's say 2x minus 5 by 3, and you substitute it here. So when you substitute there, how this problem will look like now?
It will be in one variable.
One variable,
Yes.
right? So what are you doing here? What we are saying that, see, I know that y is dependent on x somewhere. Can I use that information to make it one variable and now solve, right? Similar thing we are doing here. It just looks different here, right? Because we are not like, it's clear, it's not very straightforward here to look, but I think it's simple, right? Like you know that w is dependent on gamma. So can I remove one thing? Correct. This is what we are doing here. I hope that is fine. Either you can restrict the w to be one.
So it
Yeah.
means the upper bound for the number of mistakes will not apply here because the
Correct.
restriction on W
Correct.
is not there.
Correct. As okay, Siddharth said no. See, these were
Yeah,
the
got
conditions,
it,
right? These were the
got it,
conditions we
got it.
got, and if you are violating that, then it should not be the same condition, right? Okay, so now
But,
is this
when,
fine?
but I have,
Huh.
still I have one question. When
Uh-huh.
we had the assumption that norm of W is 1,
Uh,
then we wanted to maximize gamma.
hmm.
But when we don't have that assumption here, then we want to maximize the width.
Huh,
How do
width,
we?
width is this thing, right? It is again dependent on gamma. What I'm saying is, uh, okay, you are saying that why that one is like that, right? But this is again dependent on this one, right? W by 5. W5 by 5 is different than W by 3, right?
Yes.
Even if it is 1, this side
No,
it is
sir.
1, that is
There are
3.
two
That's
W.
5 is in the denominator, no, sir. Sorry.
Huh? Sorry.
So 5 is in the denominator, right? So it
Yeah.
will be minimized, right, for a greater gamma. If you're talking about width as W transpose by 5, W by
Mm.
5,
Mm.
so 5 is gamma, right? So
5 is gamma, yes.
we want a bigger gamma, which
Mm.
means that we'll have to minimize W by 5, correct?
Okay. I'll tell you. Okay. I think I understand the confusion now. Okay. So this fine. What is this? W transpose x equal to 5. Fine, right?
Yes.
So let's say this W is here. Fine. I'll say this W, and there is another W which is this one. Okay.
That's a different W, sir. That is
Yeah, this is a
W.
different W, right. This, let's say W prime, and this W prime transpose x equal to 3. Okay, so when I say 5 is the gamma, right? So when I say maximize gamma, what does that mean? Or maximize the margin, what does that mean? Among these 1 and 2 choices, which one should I pick?
2.
I'll pick this. This is the meaning of maximizing gamma. This
Yes.
is not the meaning that I should. You're understanding the point. It's not like we are changing these boundaries. Like we are not like. I'm not saying like this part like this. So this thing and this thing, right?
Oh, so
Or
that is understood.
uh,
When you wrote maximize the width, what is the meaning of width?
maximize the width means, okay. This is the width, right?
So maximize the
Okay.
width of W.
Okay.
Okay.
Yeah, width is what? Let's say here it is 2
Two
gamma.
gamma. 2 gamma.
2 gamma. In this case, it will be 2 into 5, right? For this red color thing, what is the maximum width, or what is the width here, or
6.
6? So again, maximizing the width means among the different solutions I am getting, among the different W's I am getting, for which W this width is maximum,
Okay.
right? And which one should I pick now?
The 10.
10 one, right? Or the corresponding to this W. Fine, right?
And here we are assuming that the norm of W and W dash both are one.
One.
Norm of W
Yeah,
and norm of W.
either you can do that, or else what you can do is you can say that this margin is one, right? Now the margin is one. In that case, this will
Divided by
be,
5.
this is your W by 5, let's say, and let's say here, okay, if since they were same, right? Like let's say, or some other thing, I can have some W by 3 here, W prime by 3 basically, and that will satisfy. Then also it will satisfy that one thing, that margin, right? I hope this is okay. You just try to understand like this. Like width is maximizing in the sense we are not actually contracting or stretching it. The margins are there, but it is respect to that or corresponding to that W. We'll have to pick one of the W's. Let's say I have 100 W's, and when I have 100 W's, I have 100 margins, right? I have to pick that W which is having the highest margin. But now if I say that all the margins are equal to 1, then in that case, which W should I pick? That is the problem currently we have to pose, right? Is that correct?
The W which we pick will be having the
Highest width.
smallest, I think, length. The norm will be the smallest for that W.
Yeah,
Because
correct.
we are,
That
we are
has to
dividing
be.
it by
Yes, right,
Yeah,
right.
that was my question.
Right,
Yeah.
right. Definitely, right. That is true, right? And that is understandable, right? If I wanted to make this one, what will be the W corresponding to this? W by
W by 5.
5, and this will be like W by 3.
W star by W dash
Yeah,
by
there'll be a different W. Yeah.
Yeah, but then the width, actually that length should be
length
like
was same. Length
as
was
minimum
same
as
one.
no, that W's what is it like, the length of that norm, right? Norm will be different, right?
But
Norm will be
W
minimum.
and W dash will were having the same norm. So if you divide one by 5 and the other by 3, W by 5
It
will
will
be
be lesser,
smaller
smaller.
as
Yes,
compared to W dash by 3.
yes, right. Fine. So is this the case now? Can I write down like this? Width of W in the sense this width is dependent on W.
W.
And what are the constraint now? The constraint
W
is same.
transpose xi yi more than 1.
Now instead of gamma, I am having 1. Fine. Okay, this is the case right now. I hope this is fine now for everyone. Why we are doing this? Uh, we have just simplified this problem, right? Initially, we were dealing with W and gamma, but we know that, let's say, W and gamma are like anyway are dependent. So uh, can we do it like this, right? Like, can we just make it into one variable? Is that correct?
Yes, sir.
Okay, good. So okay, I think that the solution is already given there for that, and that should be the function of W that we know. Okay, there is one thing I think Sir has mentioned, right? So let's say, what should be the width of W? Okay, what do you think about the width of W? I think I
Smallest
have
W will be
there,
the best
this one,
one.
right? The distance between these 2 points, right? So any point on this line, will they have the distance? Will they have the same distance on these two lines? Right. Also, yeah.
Yes, we are parallel.
Right. So, and the solution to this will be width of W is coming out to be what? What is whatever the length of W is there, 2 divided by that will be the width of W. Fine. Okay, this is the solution we are getting by which problem? Like we wanted to minimize, uh,
Maximize.
minimize,
Maximize.
Okay, I'll tell you what is minimizing. What I'm doing, minimize Z. Uh,
X minus Z.
what is this? The distance
The
between,
both parallel lines.
yeah, distance between these two parallel lines. Okay, what is
This
X
we
and
have
what
to maximize, right, sir?
is X and is Z? No.
We have to maximize width of
Maximize,
W.
sir.
We wanted to maximize the weight, but let's say what I'm saying this. So we'll have to take that minimum Z. What is that minimum Z? Okay, so let's say you have so many data points here. Which data point should I check it here?
Minimum distance.
This one, right? Which is like at minimum distance from this point, right? You
Yes, sir.
are you understanding that point?
Yes, sir. Yes, sir.
Yes, sir, it is correct, sir.
I wanted to maximize the weight, that is true, but I have to see which, okay, if I, because my uh, okay, let me see this. Oh,
Yes,
sorry.
sir, it is x minus z, no, sir. So it should be
Yeah,
like
yeah, yeah. So basically, this is like that. Oh, sorry. Okay, so let's say this is X point and this is Z point. So which one I should pick? Will I pick this line or this line? Which we generally what we should pick here?
The smallest distance between the two lines.
Correct. Right. So this is what, because then only it will be separating, right? If I choose something else here, all the data points will not get properly classified, right? I hope
Okay.
that is fine. So this is what, like, distance between X and Z. So that should be what? If I choose any X from here, the distance between these two should be minimum, right? And such that this is another problem. Okay, this is another problem. W transpose Z equal to 1. Let's say plus 1. And to that, the solution is this, right?
Yes, sir.
Okay. So now our
sir,
problem
when
was,
it's not 2 by norm w square, sir, how did
sorry,
you get the width?
this this is not the width, right?
No, the 2 by,
Ah,
it's
okay. So we'll have to solve that. This is
okay.
what, like, the solution already given in the lecture. We'll have to solve this problem. To get
Okay.
this right, we'll have to solve this problem. How will you solve that? You can either use the
Differentiate.
gradient descent or you can just differentiate. So differentiate also, but you'll have to. So you can use the Lagrangian method if you know. That will give you the solution. I think that is like, how will you pose this problem? It will be like this, no? Del of, I think, right? No, half of, I think, z square plus some alpha times,
1 minus W transpose.
yeah, anything is fine, like 1 minus, or because it's an equality constraint, right? It doesn't matter anyway, right? Yeah, this, and you will have to solve this. I how to solve this using the KKT conditions. What else are, or you can do is, let's say this is F and this is G. How will you solve that? Del F equal to lambda del G, or lambda, or you can use the alpha, but generally it uses lambda. What is lambda? Lagrange multiplier, right? Here also alpha is Lagrange multiplier. If you want, you can solve it.
I
Fine,
was
right?
able to solve without Lagrangian. Like if we differentiate the
First
F,
quantity, huh?
yeah, and we multiply it with
Yeah,
W transpose,
yeah, that is
then
fine.
we are getting plus 1 minus 1. So yeah,
You can
we get
actually
it.
add it. Yeah, yeah, that's fine. Yeah, with that also you can solve it. You can use this one, or you can, because I said this because this is constraint optimization, right? So it will be generally easier to solve this, but I think this is the very like simpler one, right? Like it's kind of like f equal to 2x square or x square something, right? That, and there is some constraint over there, right? So you can just differentiate and put that constraint there. That is fine. Hmm?
Sir,
Hmm.
explain Lagrangian equation.
This one.
Yes, sir. Yes, sir. L equal to 1 by 2
So
norm
this is
x
f,
minus z.
right? Generally, Lagrange
Yes, sir.
equation.
This part understand.
Understanding, like, there is what to explain. Like, it is the form. This is the form of Lagrangian function, right? Okay, we'll have to
Yes, sir.
see that. So how should be written is, you'll have to write your f first, and then you should use some. These are called Lagrange multipliers. You will have to use them, and then this is the constraint, right? So for all the constraints, so if you have multiple constraints, you will have to use, let's say, lambda one, lambda two, or maybe alpha one, alpha two, and like make them. So in this case, it is equality constraint. If that is inequality, right? And if it's the minimization problem, So will this hold true, or should be like this? The constraint should be like this, right?
Yes, sir.
If it is like this, then what we should do? You should make that into greater than or equal to constraints, and then by making it to greater than or equal to, you use like you'll multiply with the Lagrangian multiplier to make it equality constraint. Fine. So let's say this is W transpose Z equal to 1. Then you should do 1 minus W transpose Z and into some lambda. So that becomes equality constant. So this Lagrangian function is a function of, I can say that this objective function, this is called as the objective function, right? And what? Lambdas.
Constraint.
Lambdas, or let's say, okay, I'll write down lambda. Fine. And like all the constraints should be there, but this is the like generally it is a function of this all the data points that function. And okay, I can say that maybe if I just wanted to write down properly, it should be x and z in this case, and lambda. Okay.
Yes, sir.
Okay, you just have to, like, you'll have to study a little bit about. So have you completed your MLF?
Yes, sir.
Yeah, just okay. So I think that week 9 or 10 is there. Just have to look at.
Right, sir. I understand. Go ahead.
Okay. So, okay. So this was the solution we said for width of W. So where should I put this solution now? This was a separate problem. Now our bigger problem was this, right? This was the goal for me, correct? So how does it look like now?
Maximize this width now.
Maximize the width which is coming here, and width is a function of
W.
W that we already know, and then it is such that what will be the constraint? W transpose xi into
Y greater than 1.
equal to 1, right? Okay, so now we have okay, so this is like boil down to this problem. So yeah, now here onwards, like, this is the case we need to do, right? We'll have to solve this problem. Now there is a from here onwards we'll have to look into that primal and dual conditions, right? So let's say this is the primal problem. We'll have to convert it into the which one? Dual problem.
Dual.
Just give me a minute. I'll just plug in the charger. My okay, fine. Okay, how do you write this down now? This is not dual problem right now. It's like I know that, like, if I wanted to maximize W over this quantity, if I just uh, change this quantity to a norm of W upon 2, this will become what?
Minimize.
So it will be minimization problem over W uh,
Length.
length of square by 2, right? The similar problem, because uh, either you, because it's a inverse relation, right? If you wanted to maximize this, what does that mean? The entire ratio will be uh, reduced, right? Correct. If I increase W, uh, then this quantity has to be reduced. In other words, what I can say that I wanted to find the minimum W so that this quantity will be lesser as possible. Fine. So yeah, and here also you can see that, right? If I wanted to maximize W, that means what? My W has to be as low as possible, right?
Yes, sir.
Transpose xi into y. Why this condition is appearing again and again?
Because we want to separate, we keep it the margins.
Yes.
Yeah, ma'am.
Okay. This is the case now. Okay. Okay, now we are here again, as we are saying that how many okay, so we need to find the solution. Now this is the constraint optimization problem, right? This is a constraint optimization problem, and as I said uh, before, that optimization, right? So this problem can be solved using what? Lagrangian multiplier or Lagrangian function. How does it will look like now? Okay, again, so we'll have to solve this.
Minimize over gamma w.
So this is
Minimize
basically is a function of w, right? And this is the constant, right?
1 minus w transpose.
So this also is a function of w. Can I say that? This is also a function of w. Let me denote it by that's some different because it's a constraint one. This is the objective function. This is the objective function. Uh, and this is what? The constraint. Right. And is it a equality constraint or inequality constraint? It is
Inequality.
inequality constraint, right? Okay. Okay. Fine. So let's talk about the Lagrangian functions. So if you have the problem like this, uh, okay, maybe whatever is there in the lecture, I'll try to show you that part only, so that no confusion will be there. So okay, can you tell me if you are aware of all of these things? This was the problem for me. Or W such that g of w is less than or equal to 0. Fine. Or if you can have greater than or equal to w, that is also not an issue. But okay, I'll take this part, let's say, because it is there in the lectures. How this Lagrangian function will look like for this part?
F of w into alpha
F of
Uh,
w into
of
alpha.
w.
what is
Alpha
alpha?
of w plus
Alpha is Lagrangian
Lagrangian
multiplier,
multiplier.
Multiplier.
right? W I know, so this is the w. So this will be like f of w as it is, right?
plus plus
This is the objective function, and then plus alpha times
alpha
G of w.
g
g
of
of
w.
w, right? Now, what we can do two things. Either we can fix w and find different values of alpha, or you can fix alpha and find different values of w, right? These are the two things we can do, right, to solve this problem. I think apart from that, there is no solution to this. We can do only that too. Now we'll think about the first one, which is what? If I wanted to fix w, what do you mean by fix w? I'll choose some w, and then we are saying that this is constant. Like we'll treat w as a constant and try to solve for different alphas to get the solution that to that problem. Right? Okay. In that case, for fixed w, what we can say is, let's say, maximize this function uh, over, right? So L of w alpha, and what does that mean? Maximize greater than or equal to 0 w plus alpha u of w, right? Okay. What can you say about now here? I have already fixed the w. What does that mean? Can I say that f of w is and g of w will be some fixed values, right?
This will be infinity, right, sir?
Which one?
This max alpha greater than or equal to 0. Fw plus alpha g of w.
But
This will
will
be
that be infinity for every g of w?
No, sir.
if we have kept w as constant. If we have kept w as
Yeah,
constant.
w as okay. Let me keep w as constant, or let me select some w. Let's constant. What does it mean? Constant can be positive. Constant can be negative, or whatever the value will be. But that will define. Let's say your g of w is negative. what will happen? Will that what will be the maximum quantity for this function?
F of W.
It
Correct?
will be minus infinity, minus infinity.
No,
Yeah,
maximum will be F
okay.
of W when alpha is 0, when G of W is negative.
Minus infinity will be the minimum value, no?
Achha,
Minimum
minimum
value.
value
And
you're talking
maximum
about.
will be f of w.
Yeah,
Right?
I thought you were talking about
See, this,
maximum.
yeah, this problem is for maximizing this objective function for the given alpha, right? Because, and what is the condition of alpha? It should be positive, or it can be zero, right? But it should be positive or zero, right? So when this function will take the maximum value, if g of
If
w
g
is
of
negative,
w is if g of w is positive, then it will take infinity.
yeah,
If g of w is negative, then f of w will be the maximum
right.
value.
So there are two cases when g of w is positive, and positive g of w, how will you write it? Let's say in mathematical terms we write it like this: greater than 0. And the second case will be g of w is
Less than or equal to 0.
negative, or which w should be less than or equal to 0, right? Negative or 0, right? Somewhere we'll have to write, because it should be a continuous function. So when this is the case, when it is negative, the maximum value will be f
f
of
of
w, right? Because alpha can take values greater than, or let's say if it is any positive constant, right? Alpha is any positive, let's say 1, 2, 3, any value. What will happen? It will reduce this quantity, right? It will reduce the f of w further. And so when what will be the maximum one? When alpha is 0 into any quantity, negative or positive, doesn't matter, or let's say if it is negative, in that case f of w will be the maximum quantity, right?
Max.
I hope that is clear. Because if I have any other value for alpha uh, than 0, then it will always reduce this function when g of w is
negative.
negative. So the maximum value will occur at f of w, right? Okay, and let's say if it is positive,
Then it is infinity.
then alpha can, because alpha can take any value from which should be greater than 0. So that means alpha can go to infinity, and overall the maximum value will be at infinity.
Infinity.
Fine. So these are the two extreme conditions, right? Okay. Okay, but then I need a solution, right? I need a solution to find alpha, or w, right? Which w should I pick? Should I pick the w uh, which is bounded by this constraint, or which is bounded by this constraint, right? Is that the correct thing?
The second one we have to use.
So what does that mean? Yeah. So I need a minimum w, right? Correct. Why I need a minimum w? Because we said no, w has to, this problem will have to solve, right, at the end.
Yes.
So that has to be like as minimum as possible. So but from where I should pick? Shall I pick through this part, or shall I pick through this part?
The
The
second.
second
Second.
part, right? Because infinity, then there is no point in doing like solving for that, right? Because you can get like any other w's. We'll have to search through the space of this part, right? So all the g of w functions which are what? Negative,
Negative.
right? And what does that mean now? Now I'll have to maximize
Alpha.
alpha, right? So this was the problem, right? Maximize alpha. And what is this? This is Lagrangian function, correct? Lagrangian function. And now I'll have to solve for this. Is that fine? And for negative alpha, sorry, for negative g of w, for g of w, which is less than or equal to 0, in that case, this problem will boil down to what? Is that fine?
Yes.
This is okay?
Yes, sir.
Right. So this way, this problem will be now simpler, right? Now, how to so this problem is a constraint optimization problem or unconstrained one, right? Right. Okay. So if by looking at this problem, this will become an unconstrained problem, but this problem will become unconstrained when for the special condition of this g of w is less than or equal to 0. If that is possible, then this problem will be uh, suitable, right? Correct. I hope this is fine. Is like no issues with that part.
Yes, sir.
Okay, okay. So I think there is what more we need to solve is okay, okay. That's okay. Like you might be able to solve this anyway. That is not a problem there. The problem occurs is either okay, for multiple constraints. Shall I show you that part also, or because this is what we have seen only for the single constraint, right? This problem we have seen for the single constraint. What was the problem? The problem was this, right? At minimum of minimizing w for the maximize alpha greater than 0 f of w plus alpha g of w, and that is equivalent to what? Can we say that it is equivalent to maximum of alpha greater than 0? What we are doing here?
Changing the
Yeah, this is a like
The dual problem.
dual problem. Yeah. So why that is needed is we'll see later on. But okay, this is the case. So we can say that this is equivalent only in which case? So what is this thing? So first of all, I'll try to solve for this, right? I will find out maximum or like or alpha, which was we have done here, right? We fixed w, right? We fixed w, and then we found out which is the alpha, which is giving me the solution, and then we solve for w, right? Correct. This is one way of doing it. What is another way of doing it? We fix alpha and try to solve for w first, and then see which w or which alpha maximizes this, right? Correct. So these are the two approaches, and they should be equivalent, or the solution for this will be equivalent when
both f of w and g
both
of w convex.
f and g are the convex
Convex.
function. I hope all of you know what are the convex functions. Uh, okay, there are four, I think, four methods to or four definitions of it. Generally, we use in mathematically is I think twice differential method. Another is what?
Epigraph is
Yeah, epigraph is the general
more
definition.
than Z.
Yeah, epigraph is above that function, right?
Yes.
And another is the line joining between the 2 points should be so, or the function should be function
More
value should be
less
less
than
than.
that.
Yeah, so let's say okay, I'll show you that part. So if this function is uh, if I wanted to see that this function is convex, then you have let's say you pick any 2 points in the domain, right, or in that interval, sorry, not domain, x1 uh, and let's say this is x2. These are the 2 points in this. You just arbitrarily choose this point. What are the functions value over here? So this is f of x1 is the functional value for x1, right? I mean actual one, right? This is f of x2. Now we are saying that there exists some uh, lambda, which is or the value lies between
0 to 1.
yeah. So let's say 0 to 1, and so the line joining between these 2 points, right? I just based on this lambda, let's say I found out this point. What is this point now? This point is
Lambda x1
x1.
plus 1 minus lambda x2.
Okay, yeah, lambda x1 plus 1 minus lambda x2. This is the point. So what is the function value corresponding to this point?
F of that.
F of, let's say, I'll say that it is L. So f of L. Uh, okay, so let's say this is L point, right? But what is the actual value?
The F of L is lower. F of L is the lower point. Yes,
No,
that
no,
is F.
no. I'm just saying. I'm just naming this point. Okay, don't say that this L is lower one or something. Okay, let's say I'll
No, F
just
of
say.
L is the point where this vertical line touches the curve, right? F
Uh,
of L is lower. F of L is the point where this vertical line touches the curve. F of A.
sorry. Yeah, correct. Okay, fine. This is f of a, right? Yeah,
Yes,
correct.
sir.
This should be f of a. Yeah. So this should be okay. What is the value of this, right? So generally, what is the okay? Maybe I'll say that it is, what is this value? I'll write down
Lambda into F of
f
x1
of
plus lambda into F of x1
yeah
plus 1 minus lambda into F of
one plus 1 minus lambda, because this
F
is
of
X.
x2.
yeah. So we are actually taking the interpolation, right? And lambda times f of x1 plus 1 minus lambda times f of x2,
Is greater than F
it
of
should
A.
be greater than
Greater than
or
F
equal
of A.
to f of
F
a.
of
If this is satisfied, then it is called as a convex function. Uh, and generally, how you solve it is like, if you are given any function, you differentiate it twice, and if
More
uh,
than equal
the
to
f
0.
double dash of, let's say, x is greater than or
zero.
equal to or not, let's say greater than
Zero.
0, then it is convex. If you have like, if your function is of more than one variables, in that case, let's say f of xy or something, in that case, what do you find out? Hessian matrix,
Hessian matrix.
and you see that this Hessian matrix value or determinant of
Positive definite.
h should be greater than 0, or okay, or else I can say that okay, that is also
Positive
fine.
semi-definite.
Positive, let's say definite, because then it will be the case, right? Okay, semi-definite also is fine. That's not a problem with that. Okay. Okay, fine. I hope this is okay. Now, what is the next? Okay, this was about the convex function. What we said is this condition which we have written here, like we can interchange minimum and maximum. And if I wanted to use, and if I say that the values given by it, like the optimization when we solved it, if that is equivalent, it is only possible when f and g are the convex functions. If they are not, then this condition may or may not be true, right? That is what we wanted to say. Okay, I think okay, this is the or this is called as a duality of the, right, duality formation. Why this is useful, we'll see. But before that, we'll try to solve it, right, for this case, our case. So what is our case here? We wanted to minimize w. Which one? Right? Uh, and what is the constraint here?
W transpose
W
X.
transpose
X.
xi yi more than equal to 1.
More than equal to 1. Or can I say, let's say, g of w 0, right? Can we make g of w equal to 0?
Yes, sir.
Yes, right. Uh, Fine. So if I wanted to do it for, so till now we have just seen it only for, okay, how many constants we have seen till now? Only
One.
constraint. So if I wanted to make it like more than one constraints, how does it will look like now? Transpose or
xi
I, y,
W transpose
xi times
xi
y
xi
yi
yi greater than or equal to 1 for all I
I
I
I.
long to n,
and
1
to
to
n,
n.
right? Okay, this is a quadratic function. This is a linear function that I think all of us know. I
Yes,
wanted to make this g of w to be 0. How do you do that? So let's say
1
this is g
minus
of w. It will be 1 minus
1 minus
in
w
transpose
w
xi,
transpose
yi,
xi yi
I,
is less than equal to 0.
0, right? This is what we needed, right, for any solution to the problem, right? Because this is a our objective function is to minimize this w, so all the constraints we have to make into that case, right? Okay, so how this Lagrangian function will look like now? Lagrangian function will be your objective function first, right, plus
plus alpha plus
Alpha I.
alpha into
I,
gfw, right? So now it is I means like we have how many
I going
constants
from
here?
1 to n,
We
1
have
to
1
like
to
n.
n.
n constants, right? So
Summation of it.
right, so we make it like summation. Either you can write algebraically or you can write with uh, in the vector forms also, right? So right now I'm writing it into the algebraic form. We can make it in the vector form later on. Alpha I into 1 minus
W transpose
transpose
xi,
xi y.
y.
I hope this is okay for everyone. This is your g of I, right? Or sorry, g of w, or make I will say g of I w. So for all n, so that means we have n constants here, and on that n constants where we wanted to apply this Lagrangian uh, function. So Lagrangian function is w, anyway we know that it is a vector. What is the dimension of w?
D,
D.
D,
We are just saying that D is D because we are saying each of our data point is in D dimensions, right? And what is the dimension of alpha? Alpha is
n.
also vector, so it will be
Alpha is in n, n.
right. Why?
N different data points are there. Each has one alpha.
Yeah, each constant. So we have n constant. So alpha will be alpha n, and w will be w1 to
WD.
d, right? So what does that mean, right? So your data essentially, so each of xi is in d dimension, right? And the number of constraints
Number
or
of data points is equal
number
to
of data points will be equal
equal
to,
n.
or they are actually I equal to 1 to n. Okay, I hope this is okay now. This is clear. Yeah, I don't know why it is happening like this. Here I equal to 1 to n.
This Lagrangian will actually evaluate to a scalar, right, sir? This Lagrangian will
Yeah.
actually evaluate to a scalar only now.
We evaluate in the sense, what are you trying to say? Like you're
To
trying to
find the value of this Lagrangian, it will be a
we
scalar
don't
value.
find out the value of Lagrangian, right? We find out the solution for W, right? No, it's like you're
Uh,
talking about W's or W alpha.
but
Or,
L itself is outputting a scalar value, right? L. It may be having W and alpha as the constraints, but ultimately it will output a scalar value, right?
it will be right because yeah, but the very so how you are considering that has to be like all this W and X, W and alpha are here. What here? What is constant here? Xi is constant, right? Yi anyway we don't have to worry because yi is just labels, right? Plus or minus one. So that will just change the values. Xi is a data point which is we know already, right? The only thing we don't know is alpha and w. So these are the variables. So if you say that for particular w and for particular alpha, then definitely this L will output as a constant, right?
Yes.
So you will get like a lot of constants and you will have to pick one, right? That is the case here also. What that you wanted to say that thing, or you wanted to say something else?
I wanted to say that this Lagrangian, the value of this Lagrangian function, if we evaluate for any w and alpha, you
Yeah,
will
yeah,
get a scalar value. If
yeah,
we
yeah.
have,
But it, oh, okay, okay. You are saying that since these are the vectors, because alpha
yes,
and w's are the vectors. Ah, okay, okay. In that case, yeah, yeah, it is definitely a scalar, right? Because
yes,
this is a dot product, right?
yes, sir.
This is a scalar quantity, and anyway, this like is a summation of all this. So again, it is a dot product only. So
Yes,
this is
sir.
also scalar. So yeah, it will always be a scalar quantity, right? Okay. In that sense, it is correct. Okay, what should be the next case now? I wanted to minimize now this Lagrangian function with respect to
W
W, and I wanted to maximize for alpha.
greater than 0.
So this will be the problem like this: I equal to 1 to n alpha I 1 minus W transpose xi into yi. And this problem is now like this. So let's say this is a primal problem. How to convert it into the supposing that, let's say, these two functions are convex ones. uh, how can, and it is convex ones, right? Because
Yes, sir.
this is a quadratic function, right? Quadratic is convex function or not?
Yes, sir.
Yeah, it's a
And
convex function.
this is a
Linear.
Linear
linear function. So linear function is also,
convex.
both of them are the convex function. So the equivalent statement for this uh, will be what? Maximize
Max greater than for greater than.
0, and then minimize for w
Yep.
of w square plus equal to into n alpha I into 1 minus w transpose xi
Oh, yeah.
into yi. Fine. This is the equivalent statement, right? So in this case, what we should do here, we can fix for alpha,
Yes, mix for alpha and then solve for
solve for
W or
w, or yeah,
opposite
again
or
the same thing, right? We can do it like, either we can fix for alpha and solve for w, or we can fix for w and then solve for alpha, right? So basically, when you solve this problem, right, like, if I fix some alpha here, okay, so if I fix alpha, what happens now? The problem will be minimize w. So how to solve this kind of problem? Both of them are the convex function. So summation of the convex function will be convex,
convex.
right? Is that correct?
Yes, sir.
So now this is a problem I wanted to solve, and this is the minimization problem. What is, how to solve this problem? What methods we know?
Lagrange multiplier.
Differentiate it.
Yeah, one is differentiation. Another, iterative algorithm. Which algorithm can be used here? Can we use iterative algorithms here, like gradient descent? Yes, sir. Yes or no? Yes, yes, we can use it, right?
Yes, yes.
If I wanted it to solve by using, let's say, any solver, like computer solver, we can use the gradient descent method, and that will perfectly give me the global optimum, right?
Global
Global
minimum.
minimum, right? And
Yes,
why
sir.
it will give? Because this is already a convex function. We said that. So for different values of alpha, I can get the minimum values of w's, right? And then we can pick it. So this is how we can solve in practice, correct? Here, if I wanted to see that, anyway, this is the convex function. How to solve this then? I need to differentiate this and equate it to 0, right? So what is the differentiation of this? 2 times length of
W.
w. So 2 will get cancelled and I'll remain with w. What is the differentiation of this part? So
Alpha I.
so this is okay. This looks like how, I'll say that alpha 1, let's say, into 1 minus w transpose x1 y1
Psi by X. Yes.
plus alpha 2 1 minus w transpose x2 y2. How, what is the, like, how this will look like? We are differentiating with respect to w, right?
Yes, sir. So
So can I
alpha
say
I.
that alpha
Alpha
I
I. Summation I.
uh,
1 to N.
and w transpose xi, right, into yi? I hope this is clear. So if if you're not able to, you can just like do it, and then, or you can just write down the summation and you can write it down. So it will be
Alpha
alpha I. So it will be minus, right? Minus of alpha I, or maybe okay, alpha I into minus of W transpose,
W
not W
transpose will
transpose,
not
W
be
will
present.
go, yeah, Xi into
Y
Yi.
Y
Okay, let's say Yi. Now, and what we need to do, equate it to
0.
0, and that means this minus sign, if I say it here, that will be like, what is your W here?
W will be the summation of I equal to 1 to n.
Tn alpha
Alpha
I
I
becomes
Xi Y
Xi Yi. Okay, that is the thing, right? What is the dimension of X here? The dimension, this is basically either 0
Plus
1,
one minus one.
plus 1 minus 1, you can put it, or yeah, generally we are actually saying for negative and positive class, and that is there. And alpha, what is will be the value of alpha?
1 into n. It will be n into
No,
1.
it should be greater than or
Yes,
equal to
yes.
0.
Greater than 0. Greater than or equal
Ah,
to 0.
right, yeah. And this will be what then? This W will not be a normal W, right? This is what? The optimum
W
W.
star. Yes, sir.
W star, right? Okay. And what need to do then? Like if I got this W, then
Use that W to find the test label of the test. This will be the optimal W which separates with maximum margin.
this will be the optimum one, which will be separating the maximum area, right? So this will be that this problem, maximum of alpha greater than 0. What is it then? Can I say the alpha I into
Xi Y.
hmm? Okay, fine. Let's. Okay, I think we I jumped it. Okay, I'll just will okay. We'll think about it. Okay, so in vector format, how this will look like W star? It will be X Y alpha. Okay, is the vector form of this W star. Fine. You can think about this because X will be what?
D into n.
D into n. So each of it is actually because each of Xi I said is in RD, right? How many I will be there? How many data points are there? N data points. So this vector will look like this. Okay. This X vector. What about Y? These are the corresponding labels, right? So how this Y will look like?
The diagonals.
Diagonals. It will be Y to
Yn.
Yn, and all others will be 0. Why it is like that? Because if you just multiply this X into Y, you will get like x1 y1. You should get x1 y1, right, every time. X1 y1, x1 y, like that. And what about alpha? So the alpha vector will be 1 to n, right? Okay, alpha 1 to alpha n. So this is n cross D matrix.
D cross n, sir.
D cross n.
Yeah, D, okay, D cross n. This will be
N cross
n cross n,
n.
and this will be
N cross 1.
n cross 1. So basically, if you think about this part, the summation part, because if you take a summation, it will be a scalar, right? Scalar value, or okay, anyway, it will be a vector, but uh, how does it will look like? What vector? Okay, I shouldn't say scalar. It should be a vector, but
Vector, sir.
are you able to see that vector in this case?
Yes, sir. Xi is RD. That is why it's a vector.
Right, so it will be a vector, and that means if I just do it here, X is D cross n, Y is
N
uh,
cross n. N
cross
cross
n. So if this is same, then the multiplication of X and Y will be D
D cross
cross n, and if I multiply with n cross 1, so this will finally will be giving me
D
D
D
cross
cross
n.
cross 1, and that is what the desirable thing, right, for me. Okay, Fine. So this is the vector format solution for me. What was our objective previously? What is the Lagrange function? Lagrangian function. It is half norm of W square plus
plus
alpha I GW.
summation of
hmm?
summation
Summation.
of I equal to 1 to n
Yeah,
Okay.
some more
In this case, okay. Let us write this one. Okay.
alpha I
I into
1 minus
1 minus
W
W
transpose
transpose XY.
y. Okay. Fine. Fine. That is okay. Okay. Now, what I'm saying is,
we have the optimal W, so substitute it.
so what is the optimum W? Is okay. Let's say if I wanted to write it into the vector format, it will be like xy alpha, right? So how does this will look like? Alpha into 1 minus W transpose xi and yi. You'll have to make it vector, make that also into vector form. And if I substitute everything, what should be the Lagrangian function? So okay, you can try it later on. Okay, you'll just have to make this also in the vector format, and then only you should add it, right? Or you should substitute it. You should substitute this. Where you will substitute? Here also, and
And W, yes.
right, wherever W is there, you just put this value. What you will get is alpha transpose. There is like into 1 actually sir has written. So that is 1 is for what?
Vector containing a
Column.
1 into n.
Yeah.
Yes.
1 n times.
Yes. Okay. Minus half uh, half times
XY
xy alpha.
alpha transpose XY alpha.
You'll understand it why this will happen. So you if you try it, like you just substitute there, you'll get this answer. So this will be your answer, right?
This alpha will be the optimal alpha, right, sir?
Yes, because we are just considering that W star as the optimal solution, right?
Yes, sir.
Okay, so this is the case here, and if you just what do? You just open that bracket. How does it will look like? So xy alpha transpose into xy alpha. How does it look like?
Transpose Y
So
transpose
this part is x transpose
Y
y
transpose
transpose x
X
transpose
X
into x
XY Y
alpha, right? Xy alpha.
half divided by 2.
Okay, 1 by 2. Yeah. This is a Lagrangian function, or this is the uh, this basically we are actually trying to find out. This part is for so the
But sir, we have taken we have fixed alpha here. Now, when
yeah, yeah,
we differentiated with respect to W, we fixed alpha. We
yeah.
have
Then
not. Okay, this is max, sir. Yes, yes.
yeah,
Then it is
you
right.
you will have to find out like all the set of alphas for which this is true, right? So you just actually picking it one of the alphas, right?
Okay.
Which gives the maximum, or you pick the maximum alpha. So what are you doing generally? You get it right? I don't know. Okay, so what you do, you have, let's say, alpha values as, let's say, I'm just giving you the examples. It might not be the same, but let's say 1, 5, 9, and 10. Okay, for this one, okay, I fixed alpha equal to 1. I found out some W star value. Okay, I don't know. I'm just saying like arbitrarily 6. For this 5, W star is 5. For this 9 is W star is, let's say, 7, and for this 10 W star is, let's say, 4. Which one is the, or okay, maybe I'll say the 8. Which one you should pick?
5.
This
Where
5.
is
Right?
W 5? Yes, minimize that. So for W star equal to 5.
Why this is like that? Because our problem was minimum of W, finding out the minimum W, such that that Lagrangian function will hold, right? Correct.
Yes, sir.
And then what we saying is that okay, these are the values for different while fixing different alphas. And what is the outside problem? I have to find that alpha which is maximum for that minimum value of W, right? So I will not go and pick this 10. Why? Because this is not the minimum value which are getting. This is the minimum one corresponding to the maximum value of this. Fine.
Yes.
If let's say if this was the condition, which one should I pick?
Fourth.
Huh? No. Which alpha should I pick? Alpha
One.
1 or 5? One, huh?
Yeah, one. Because we want to minimize W.
Right. And now let's say if this is the case, then
5,
1.
5.
5, 5.
Maximum. Yeah, sorry.
Got it? Now I hope you are able to understand this, like this part, right? Why this condition is there. So you fix alpha, you find the corresponding W star, and then you pick that alpha, which is the maximum one, right? Among all of these minimum values. Fine, right? And like that means what? Like that again means that you are choosing what? Like the alpha and W both, right? You're getting both values at the same time. This is what, like, and the primal problem was what? Minimum of W, and we are maximizing alpha. So in that case, what we are doing, we were fixing W's, right, and finding the maximum value of alpha, right? But then that case, what is, like, it's tough, right? Again, in tough in which situations now? I hope this is clear for you. This is the primal problem, and this is the dual problem. Shall I write it down? Like, what is the primal problem? I think we should had previously this one, right?
Why is the primal tougher, sir? Why is the primal tougher
It is
than the
not
dual?
tougher. It is not tougher exactly. But see, when you find out for maximum, right? Any maximization problem is generally is unbounded, right? For like convex, if you have the convex functions, which one is the better thing to do? Finding out the maximization thing, or doing the minimization one?
Minimization.
Correct, right? And when we say that, I know that f of w is quadratic, g of w is linear, both are the convex functions. So which one is easier for me?
First you
Obviously
find the
the right, and then you pick. So that is why, see, maximum, finding maximum alpha greater than 0, then it will be, you're getting solution very late. That is one of the things. What else is there? So I think sir has said, like, 3 points sir has mentioned. I will also write down the same things. One is what? It is about the dimensions also. So uh, okay, dual constants are easier. Why that is easier, I said to you. So one of the things is easier. Why it is easier? Because anyway, whenever convex functions are there, finding out the minimum is the sensible thing to do, right?
yes, sir.
That's why it is easier. What else is there? Dual variable dimensions are
Another.
Rn plus, okay,
Rn.
plus. What is this Rn plus? Because
Positive.
this thing, right? We are not actually searching for all the values which are in the negative side. So at least, like, we have cut down half of the values, right, at the same time. Correct. uh, I hope this is fine. And in the primal problem, we have to find out for, like, when I say fix W, I'll have to fix, like, we'll have to find out for how many W's there, like almost all, right, whatever there are, like positive, negative, everything. So that is another thing. So primal is working along with uh, d dimensions, and this is along with Rn plus dimensions. When d is much larger than n, then this is the uh, easier problem to solve. When okay, which one?
Dual is the easier one, right?
Yeah,
Dual.
dual is the easier one, right? This is the dual thing, and this is the primal thing. So dual will be the easier one. Another thing why it is easier, I said, is because if the both of the functions, right, or whatever the function, Lagrangian function, if it is convex, definitely it will be the easier thing. What is the third one? Third one is about the kernel. So what does your kernel do generally?
So there is X transpose X.
Yeah, so kernel is, when you do kernelized version of it, generally kernel is, you find out this kernel, right? This is your kernel. Right.
I just
So
substitute x transpose x with kernel function.
yes. So if I wanted to solve for kernel functions, then or kernel function in the sense, what does that mean? Is that if your data set is the boundary in the lower dimensional subspace is not linear,
Not a linear.
and if it is linear in the higher dimensional space, in that case, what you do?
Substitute x transpose x with
Yeah,
kernel
you
function.
find out the kernel and then you try to solve the problem, right? Generally, that is what we have done from PCA, from the linear regression, and now also, right? Whenever your solution, right, if it is not in PCA, what we said, if it is not linearly separable, or right, okay, let's not say linear separable, but if you are not able to find out the linear solution there and the lower dimensional space, what do? You go to the higher dimensional subspace and find out or perform PC over it, right? Similarly, in the regression also, you don't get that solution on the lower dimensional space. You go to the higher dimension using the kernels, right? Kernel helps you. How they will help you?
By
Find the dot
converting the
product in the
problem of
higher way.
Yeah, you don't need to explicitly, uh, you know, do this calculation, right? X transpose X.
yes,
It will
just
provide
find the kernel
kernel, yeah, and that will give you the kernel variable.
matrix,
Yeah.
kernel matrix.
Okay. I hope this all are fine. Uh, okay. Maybe there is one.
In the primal one, we cannot find such a form where
Yes.
where we can convert it into kernel, right?
Yeah, yeah. It is not. That solution is not there. Like you will not be able to find out. That is why dual is good to solve here. I think there are one thing I just mentioned previously, about the KKT conditions, right? What are the KKT conditions? Do you remember? One is what called the stationarity condition. I will just try to give you the overview of it. Anyway, sir has mentioned it properly anyway. What is the, let's say if you have this Lagrangian function, what is the stationarity condition? Equal to 0, right? Second one is called as uh, complementary
Slackness.
slackness. What does that mean? It provides you the like soft, okay, in this case it's soft margin here, but it what it does is whatever the inequality constraints are there, you can make them an equality constraint using the Lagrangian multipliers, right? uh, I hope this is fine. So let's say what is generally our problem is, let's say this problem is like this: minimize your f with the constraints, let's say g of I, let's say greater than or equal to 0 or any other value, let's say. Okay, in this case, this will turn out to be what? Del f plus, okay, how does your
Uh,
Lagrange will look like? Lagrange in this case will be f plus, let's say
alpha
lambda, okay,
times
alpha times g
gh.
of I, right? Okay, whatever, like, okay, g of I, or you wanted to say, I don't know what. Okay, let's say f of w and g of w. In this case, it will be this
Less
alpha.
than or equal to 0, right? So g is
Huh? Anything is fine, right? You can make it anyway. If this is the case, also is fine. Generally, in minimization problem, the constraints will be like on the upper side, right? Then only it will be happening. Otherwise, it will not, right? Correct, na? If you think about the minimization problem, if your constraint is saying that it is like you should see the space which is higher than this, or that will be fine, or lower than this, that will be fine. Generally, it is, I think it depends actually. It's not the norm or something. You can make it like, how will you change this? If I want to change, I just use the negative of this, right? That's okay. That is not a problem here. The thing is, then this will become del of f of w plus
Alpha times del of g of w.
W equal to 0, right? Okay, this is one thing. Complementary slackness, what does it do? Alpha g of w, it will make
Equal
us
to 0. Equal to
equal to
0.
equal
0.
to
0.
0. This is a complementary condition, and there is one other condition is primal feasibility, and the fourth one is dual feasibility, right? So these conditions actually are not like generally it's, let's say if this is a function of w and is like w1 and w2 are greater than 0, right? This I think all of you have known this. So this is the same. This is the dual feasibility condition. What about the primal feasibility condition? I think primal feasibility will okay. We have to write it down like in that format only, right? Okay, you can just refer to the MLF notes. Okay, I think you will get it. This is not, so we cannot write it here. Like we'll have to write it in that format only. I think then only I'll be able to write down. But okay, these are the four conditions which are there in KKT. Uh, Among those, we use two here, and how to use that I will just show you, and that we are actually going to use in the next week. What was our, okay, before going to there, what is the solution, optimal solution we have found out? Yeah,
Equal to alpha I alpha star, right, sir?
yeah, alpha star. Okay, okay. This is also the optimal one, right? This is the solution. uh, okay. Soft margin, okay, support vector maybe will support vector. I'll, okay, just give, I'll give you the glimpse of the support vector. Basically all the soft margin classifier maybe we can discuss in the next uh, chapter, right? So what is the Lagrangian function? What is the primal here? Primal here will be min over w
Max over alpha greater than
0 f of w plus alpha
alpha times g of
g of
w.
w. What is the dual? Dual
Max
is
alpha
max
greater
over
than
alpha 0
greater than mean over w.
w f of w plus
Alpha
alpha
times
g of w,
G
right?
of W.
Right. And w star will be the solution for primal,
primal
and here
alpha
star will
alpha
be the
star.
solution for dual. Okay.
W star will be in D and alpha star will be in N.
N,
So that is why if D is much greater than N, then it is beneficial to solve dual.
right. Okay, yeah. So what is this then? What is the maximum value of the function will be there? F of w star plus alpha.
Alpha star into G of
No,
W.
not alpha star now. Let's say we are
For
finding the primal.
primal.
For primal.
Okay.
Basically, okay, what is our aim? What we are saying that the solution for primal should be equal to solution for
Solution.
dual, right?
Dual, right.
If it is not, then there is no but how to prove that, like, or how to say that this is going to be, we only already said that if these two are the convex function, it is going to be like, it is going to get the same thing. But let us say it is not. In that case, I have found out w star as the solution for the primal and alpha star as the solution for the dual. Then what will be this value?
Max or alpha greater than 0, right?
Max of or alpha greater than 0, right? And here it should be equal to min over
W uh, f of w
plus
plus
alpha,
alpha star into G of W.
right? Okay. Now what else? What is this part now? We already said, right? If g of w is less than or equal to 0, what is the answer to this problem? What is
F
the
of
maximum
W
value?
star.
Right.
F of
If this case is if g of w star is, and that is there, right? I think we somewhere I written it. This is the case, right?
yes, sir.
So we were trying to do that, and in that finding, we
But
said
sir,
that
about what is the require here? We have not mentioned that G of W star is negative, right? G of
No.
W.
Okay, we constrained it. No, you only said right now.
Yes, yes, sir.
This is the problem we are trying to solve.
Yes, sir. Yes, sir.
This was the objective function. These were the constraints. Correct.
Yes,
So
sir.
all the constraints are in that format, less than or equal to. If they
Yes,
are
sir.
there, what does that mean? We are doing the same thing right here.
Yes, sir. Yes,
So
sir.
if that is less than 0, less than or equal to 0, then definitely the maximum value of that function will be what? F of w star. And that
Yes.
should be equal to, what is the bound on this value? Minimum of w, f of w, plus if I use this w star as a solution here, if I put it w star there, that be the will that be more than this, or will that be less than this? If I put w, okay, if I just write down f of w star plus alpha star g of w star, uh, this quantity will be, okay, first of all, this quantity will be less than this or greater than this part.
Mean, right? So it will be lesser than this.
Okay, lesser than which one? Okay, let's say I put it like 1 and 2. So is 1 less than or equal to 2, or
2 will be less than 1, right?
think about it again some more.
2 will be less than 1 because W star is minimizing the value, right?
Minimizing the value of that
Of the
function.
function. Yes, sir.
But no, okay, so this alpha star, we have found out the solution uh, by this, right, from the dual problem. So in that case, alpha star was the maximum thing, which was like we have chosen that maximum alpha, which is actually minimizing this value. So okay, with in the case of upper bounds, what do you think about it? Okay, think about it. Actually, this is the answer, correct? Which is like this quantity is less than or equal to this quantity. Think about it. Why it is like that? Right. So you can think it that. So I'll tell you. This will be, the upper bound should be equal, or I can say that it should be less than or equal to f of uh, w star plus alpha star into g of w star. Okay, you can think possibly, and then we can discuss it. I'm just writing it down here. Okay, this should be less than or equal to. Why it is like that? We can just think about it maybe after a few minutes. What about this? This will get cancelled. What we stayed with now is the case.
Alpha star is more than equal to 0.
uh, right, so this case is so let's say alpha star and g of w star basically is greater than equal to 0. In this case, this is going to be equal, like if I wanted to use the equality constraint, in that case either alpha star will be greater than equal to 0, or g of w star will be greater than equal to 0, right? If I just purely look at into this equation, these are the two cases, right? But we already know that g of w star will, right? This was a constant, initial constant. If I know this part is correct, then in that case, uh, what is the condition now?
Alpha has to be 0 then in that case.
Yes, it
Because
cannot be less than 0,
Right,
so only 0 is left.
right. So alpha, if this is the condition, then what happens? Uh, and what are the condition on alpha? Alpha star, it
More
should
than
be
equal to 0.
0. So both these can be like both this will be satisfied in which case?
Alpha star is 0.
First of all, in this case, right, equality case, right?
Yes.
Otherwise this is not this is not a feasible thing to do, right? You are increasing the alpha more than this, and you are reducing g of w star, or which is less than 0. Both, see, if this is a positive quantity and this is a negative quantity, this will not hold true, right? Never is possible, right? Correct. Is this condition is not going to be possible. the only condition which is possible is that either this quantity is 0 and this will become the equality constraint, right? Or this quantity will become 0 and this will become, that is the only possible case uh, when we had these two constraints, right? Because if one of the constraint is negative, right, and I know definitely that alpha is not going to be negative, and I know for sure that g of w star is negative. If g of w star is negative, in that case, will this hold true? That
No.
No.
greater than condition will not hold true, right? If you have these two constants, the only thing which is possible is equal to
The
Zero.
equality.
0. So that means when I multiply with Lagrange multiplier to any inequality constraint, what does it do? It will make my equation to this part, right? And this is what the complementary slackness condition, which we talked about earlier, right? This is the complementary slackness condition, and okay, see, this is what already we have seen, right? In KKT conditions, uh, we should have this kind of constraints. And why this comes up, we have shown here, because this, in this problem, it is not going to be possible that alpha star into g of w star will be greater than 0, right? Because I know for sure that g of w star is less than or equal to 0. So the only condition possible is when j of w star is equal to 0 or alpha star equal to 0. So we can say that equality possible, but greater than, like, strictly greater is possible? No, right? I hope you understand the argument here. Uh, okay, this was the thing. Now, what does that mean? Okay, okay. I'll just talk about support vector in like few minutes, and then we'll stop. Uh, what does, okay? Currently, whatever the discussion we have done, that discussion is about what? Maximizing the margin, correct, na?
Yes, sir.
Maximizing the margin. Okay. Let's say you have this data points here. Okay. And I think when we started this discussion, somebody has told, I remember that we shouldn't take the points which are away from this W transpose X, right? Suppose, okay, sorry. Let's say, what is this point? Let's say if it is, this is W or
W transpose x equal to 0.
0. And what we tried to do is, we tried to maximize the margin, right? And which margin should we consider, or which are the points we should consider to, so what you said, I think someone has said already, right? So or we should pick that margin which will have this distance as the
Maximum.
distance as maximum or minimum.
Maximum distance.
Okay, and okay, maximum margin, maybe I'll say, or if this is x is fixed over this, then the, and if it this is z, then the distance between x and z should be
The minimum distance between x and z.
right, no? Yeah. Okay, so support vector machines, what it does is, uh, it will just take what? It will take the points on the this hyperplane, right? And this called, and this with respect to this hyperplane, we decide the margin. And what are these points talking about? These are the points which are the
Closest to
closest to,
the
yeah, closest to,
origin.
yeah, origin, or closest to this line. Fine. If you find those lines, you just sorry, if you find those data points which are closest to the closest from the origin, we will take those points only to find out the margins,
Margin.
and we don't care about uh, other points, right? And what does it will, like, what do you achieve from that? We don't care about this. What do we achieve from that?
We decrease dimensionality reduction.
Yes, right. So we don't need to do a lot of, okay, because this W star was dependent on what? If you have found out the solution here,
Alpha into x into w.
right? So alpha, okay, this was x y alpha, and if you reduce this or we just found out only those data points which are actually related to that hyperplane, right, or which are very nearer to that uh, uh, origin. If you just use that one to find out this my w star, then what we are actually achieving is we don't need the other data points to find out those hyperplanes, right? And that is what actually the support vector machine do. And these are the support vectors for and what are why this called as support vectors? Basically all the data points are the vectors, right? So these are the data points which are actually contributing for defining the margin there, and hence these are called the support vectors. And that is what is a support vector machine algorithm. We'll have to see a lot of things about it, maybe when we see about soft margin classifier here, or soft margin SVM. We will have anyway week 11 coming up, so we'll discuss more about that there. You can study for this. There's not like a different thing, but soft margin we'll discuss it maybe next session, right? I haven't touched upon like a lot of things like related to soft support vector, but I hope you can just whatever discussion we had today, you can build on that, right? Is that fine? Okay, maybe we can
Yes, sir.
talk about it later on. That's not a problem. Okay, uh, fine. Any other things? I hope this is fine for you. I have just summarized whatever is there.
So the
Like,
can I ask a graded assignment question from
yeah, yeah.
last
Grade
week?
assignment, or you said up to some about something
Yes,
about that
regarding the current
activity.
week also, there was a in first lecture itself, there was a question of activity question. I think first lecture.
Okay, okay. Just a minute. I think about that we have discussed it, but let us see. This was the question, right? Given a linearly separable data set, consider two different runs of the perceptron. The weight vectors obtained at convergence were W1, W2, respectively, for these two runs. The margins
Yes.
for these two classifiers are 1 and 5. Which of the following
So
statements?
5 is better, definitely. So W2 is better. This is clear, sir.
Right,
W2
no?
is better
Yeah.
choices.
Now we have done that like entire thing. So I think that is the case, right? I hope that is not
Second question I was asking about. Yes, sir.
okay. Okay, the margins for this is okay, maximum. Okay. In the previous question, let W star be the optimal weight vector with the largest possible.
Optimal weight vector they are saying is W
The
star
different,
and it
yeah,
has a margin of 10.
10. Okay. What can you
And
say
then
about the number of mistakes?
in the first and second. So in the first, that is referring to question number 1, sir. There are 1
Yeah,
and
yeah,
5
yeah,
now.
yeah, yeah. Yeah.
So they are saying that the optimal W star is 10.
Mhm.
And what they are saying is that even if we reach to W which is having a margin 1 and 5, we'll take maximum 4 mistakes only. Because the optimum W
Okay,
star is 10.
I think see the number of mistakes, the maximum number of mistakes are bounded by what here?
The optimal W.
Yeah, so it should be 20 square by 10 square, right? So
Yes, sir.
400 by uh, so it should be 4,
400.
right? 400 by 100 is just 4, right? So it should be
Yes.
4. So what is it like? Anything it is specifically okay.
So
One option,
even if we reach, we can reach to any W. Ultimately, we'll take maximum 4 mistakes
option B
only.
should be correct, na?
Yes, sir. Yes, sir.
So what is the answer here to this question?
So actually, I thought
B
the
only.
answer is different.
No, I think this is fine, right? What is the issue here?
What I thought was because the alpha in case of the
Acha,
1 and
okay,
5
you
is
said like
different.
okay, okay, okay. So 20 square by 5 square you did, and 20 square by
Yes,
1
sir.
square
Yes,
you
sir.
did. Ah, okay. And then the question is, okay,
416, the first option.
okay, okay, okay. No, no, no. I think the see, we'll have to think about because these were the two runs, right? like two different runs of the perceptron algorithm, and they found out some weight vectors, obtained convergence. Okay, I think this question is like, yeah, a little bit, maybe I'll
So
say
what they are saying is whatever W we find, ultimately the number of mistakes which we will make
the, yeah, it
will be
depends on
depending on
W.
the alpha of the optimal vector, optimal W.
Yeah, correct, correct.
So
Yeah,
by perceptron, it's not necessary that we'll get the optimal W, but whatever W we get, the upper bound for the mistakes for that W will be the will depend on the alpha of the optimal W. And
Gamma.
optimal W
huh.
perceptron may not find, but optimal W we can find with this support vector, I think, algorithm.
The support vector we haven't discussed yet, right? So whatever we have done is like, yeah, okay. That is what we are trying to say. Yeah, this is the correct one. We wanted to maximize the margin as, yeah, as possible. But okay. So yeah,
So
with support vector machine, you are able to find out
optimal
the
W,
optimal
optimal W,
W, right? That is true. But with perceptron, we may not be able to find out the optimal
optimal
W.
W.
But anyway, the number of mistakes it can happen will be bounded by r square upon gamma square. So
And
what
where
we are
gamma
saying
is the
is,
optimal to gamma. Where
yeah, correct, because we say that gamma should be the highest margin, right? So that assumption we are actually making, right? So this doesn't have to calculate every time, right? Correct.
yes.
Yeah, correct. What else is there?
Uh, and graded assignment of 8th week, sir.
Eighth, eighth week,
Ninth week.
ninth is okay. Is it done like grade assignment? Okay.
Last, go down, sir. Down. Yes, sir. This question. It is about logistic regression. They are saying that the brown line is the one for logistic regression. But is it the ideal line for logistic regression? Logistic regression will be somewhere in between these two orange and pink points, right?
It is
The,
there,
the,
no, but it should no, it should be going through
it is
the,
closer to the orange dots, sir. It
no,
is
that is
closer to the
okay,
orange.
but it should be going through the zero vector, right? The decision
Okay,
boundary
right,
has to
right.
go through it. It cannot move here and there, right? Because
But it can tilt, na? It can tilt towards the pink
see,
dots also.
it can tilt, but it is not going to be like, the moving from zero. It should be going through zero, right? Because
Because we are
anyway,
using the maximum likelihood to find this brown line, right?
yes.
So, so using maximum likelihood, this brown line will be almost equidistant between the pink and the orange points.
Yeah, that
But
is
here it
okay.
is
No.
closer to the orange points.
So this is not the argument about the which is the closer. That is not the thing. Like it's just asking, like, let's don't worry about the accurate thing. No, just think about like within the blue and brown, which one you think that will be the decision boundary, right? So in that case, it will be brown.
What I chose was none of them was the decision
So
boundary.
none
That's
of
what
them
I
is
chose.
none of them is also there. Okay, none of this. Okay, so I can't argue about this thing. Right. So I don't know. Like, see, we cannot say that. Maybe this is also the possible one. Okay. How do you find out the decision boundary in the logistic regression case? You calculate W
Maximum
transpose X.
likelihood. Maximum likelihood.
Yeah, maximum likelihood. But those likelihood is for what? Uh, will that give me the decision boundary, or will that give me the probabilities?
Maximum likelihood will give me the ideal line which is separating the 2 points.
What is the solution there for logistic regression? Maximum.
1 by 1 plus e to the power minus w
No, that is a
transpose.
logistic function, right?
Oh.
uh, the solution. Do you have the solution for that? The closed form solution for W?
It is something I think
I don't
uh,
think we have any closed form solution for W there in logistic regression.
We don't.
right? No, if I think so. No, it's not there. So we do not get actually from.
So it is something like summation xi into yi minus.
No, no,
There is some solution, sir.
no, no, no.
Summation.
Listen.
Yeah, we have to perform gradient descent or something because
Uh,
there's no closed
We
form solution.
yeah, we so whenever there is no closed form solution, then we have to perform gradient descent, and gradient descent will not never give you the optimal solution, right?
So can you go downwards?
Uh, so this is the
They have given a solution for W
okay.
star.
Let me see this thing, right? This is the something, and then we found out some del of this, and then see this is a gradient descent
It's
one.
a WT.
Ah,
Okay.
this is not the solution, no.
Okay. Right. Right.
Gradient descent that see that doesn't guarantee you the like where you can actually stop in between
Gradient
also.
ascent actually. Gradient
Ah, sorry,
ascent.
ascent, yeah, this is a gradient ascent rule, but still it will
It will reach the maximum, right, sir? It will converge to maximum.
it will converge to the maximum, but again, see, that is what, so the solution shown here, will that be the final solution or will that be the solution? See, there are some methods. If you shouldn't go to, if your updates are I think we have seen in decision trees, right? You can actually do pre-pruning, or pre-pruning in the sense we just stop at some point of time, right? So let's say your updates are not going uh, like you're not getting the good amount of updates. What do you mean by good amounts? Is like, let's say you are doing the gradient ascent, right? And suppose your solution is at 100. You started with 1. After first iteration you reach to 25. After second iteration you reach to 50. After third iteration you reach to 75. After fourth iteration you reach to 76. After that you reach to 76 point something. After that, like that, that is possible, right? It
Yes,
depends
sir.
on your step size and how this gradient value is like doing it. So do you want, see, it is, I'm sure that we can actually eventually find out uh, the maximum one, right? If that is a convex function. But if I don't want it, if I'm like satisfied with, let's say, we stopped it after 10 iterations, or we stopped at, like, we just give them some threshold, and we say that okay, I don't want the like exact solution. Suppose the exact one is, let's say, at 100, and we stopped around at, let's say, 99 something. Okay, we use that W to be your optimal one, and you just draw a boundary. Maybe this is one of the solutions, right? It might, I'm not saying that it is the correct one.
Okay.
That is possible.
And a blue line is not correct because it is not
That is
passing through the
sigmoid function.
origin.
No, no, no,
And it,
not that thing, right? Generally, descent boundary of the logistic regression is linear one. It is not any other, right? This is
so what is
actually the,
the so it brings to the same question, sir. Last lecture
yeah, I
also.
said no.
What is the kernel? What is the use of that kernel in that or
Kernel is, it will transform, right? And after transformation, if you apply the any algorithm, right, it will find out you the linear decision boundary only in logistic
okay.
regression case. Hmm? This is a sigmoid function actually. So if you plot the sigmoid function or the logistic function, it will look like this.
Okay.
Yeah, and if you set, let's say, if you set a threshold here somewhere, uh, it will actually uh, accordingly it will give you the positive class or a negative class,
So
but
this
this is not a
blue
decision
is
boundary.
not a logistic regression line
No, no.
because it is not a straight line. One.
Yes, yes,
And second, it is not passing through origin. That is second
but I
reason.
think the second we shouldn't reach, right? Like once you know, right, that the form is not like that. If it was a line, then we can pick up, right? But this is not the one which is there, so we shouldn't think about that also. Okay.
But sir, in one lecture, the point 5, if we take the point 5 as the threshold,
Threshold, yes.
yeah, the horizontal
This,
from black
okay, that sigmoid function gives you what?
Probability.
probability.
Probabilities,
Okay.
right?
Of
That is
which
not
class it
giving,
belongs to.
yeah, but it doesn't give you the line or
Distant
the
boundary.
separable, right? Yeah, decision boundary. Correct. Decision boundary is that which actually classifies uh, the thing, but how to decide which one we should pick is dependent on what the probabilities. Decision boundary is linear means what, this one, right? W transpose X, that is a decision boundary, right? Okay, this thing, actually this thing gives me a decision boundary, the W transpose X, because this probability is a function of what, this W transpose X. Only the thing is, to calculate this probability, I am using some different functions. So there are different functions, sigmoid, ReLU, some other like step functions are there. Which one you should pick, that is your case. You just put the threshold and just say that whatever above is this line or above this point is, I am saying that this is going to be positive class and negative class. But that is
So,
not a decision boundary.
what we have done is we have made the probability and then we have entered it into maximum likelihood thing.
Yes.
So we should get an ideal decision boundary, sir. I mean, why I don't understand why we are not getting an ideal decision boundary, because it is not closed form solution. That's why.
Yes.
Okay.
Closed form solution is what, let's say W star is equal to XX transpose inverse XY. It was in linear regression case, right? So where I can actually put the vectors and I can find out the actual W star. Or if you have X square, what is the closed form solution for the, like if you wanted to find it, like differentiate, if you can differentiate and equate it to zero and you get some solution for it, right? These kind of things, if you are able to do it, then it is called closed form solution. Here I am not able to solve this, no. There is no chance that I'll get some W.
Okay.
Gradient ascent or gradient descent, the point of them is using is because why we wanted those iterative algorithms, because I am not able to get the closed form solution. One, second is what, the calculations, right? Even in linear regression case, why we use gradient descent there?
Because the matrix is too
Yeah.
large to calculate.
Yes. Yeah. So these are the two things which are actually problematic. To solve those problems, the iterative algorithms will help. Got it?
Okay.
Okay. I hope that is okay. We'll stop here then. Good night, everyone. You just go through the lectures once more, okay? All the like remaining ones, like maybe I didn't touched upon all, like last
Sir,
one or
I think the deadline for all the remaining weeks is 30th only. 30th only.
30th March.
So
I
can
think
it
for 10
be
and 11. 10 and 11.
12 is, I
can do
think,
it in 12
April.
also.
No, it's April.
12 is in April. 10, 12 is not here.
12th is in April?
Yeah.
Because I thought it is in 30th March only,
No,
I
no,
think.
no, no, no. 12th is not there.
Okay.
Okay. Yeah. Bye bye. Yeah. Good night.
6th April.